Alrighty, so a very common question we end up with is always circular functions. The reason for this is that since cosine and sine are both defined as on the unit circle, then they're really useful at modeling any sort of motion that's circular. So you can think of a Ferris wheel or a wheel on a car, anything in which we're interested in tracking a point around the circle. Then using cosine and sine functions is just perfect, because as well as modeling triangles really well, they also model circles really well. So the power of these functions, which means they come up all the time. So the diagram shows a water wheel of radius 3.5 meters, where P is a point on the edge of the wheel, and D is the height of point P above the surface of the water. The center of the water board is always 3 meters above the surface of the water. It rotates 4 revolutions per minute. 3 seconds after the water wheel starts turning, P is at its maximum height, 6.5 meters above the surface of the water. Determine the maximum and minimum height of point P. So step 1 is just the maximum and the minimum. You can see here that at the maximum point it's going to be 3.5 meters on addition to the 3.3 meters from the water level. So it's going to be, for the maximum, it's going to be 3 plus 3.5, which is 6.5 meters. And for the minimum, it's going to be, well, the difference between these two, which would be 3.5 meters. I'm sorry, 3 meters minus 3.5 meters. So it'll actually be under the water, negative 0.5 meters. Alrighty. So the height of the point P at time t seconds can be modeled by a function of the form d equals a cos b bracket t minus c bracket plus d. That's a generic formula. Sketch a graph of the function for 1 revolution. Alrighty, so it says that it rotates at 4 revolutions per minute, right? That means 1 revolution is going to be 1/4 of a minute every 15 seconds, which is our period, because the period is how long it takes for the thing to repeat. So what we say is that since the period is 15 and we know that it's equal to 2 pi over the absolute value of b, well, we can solve for that. B is going to be 2 pi on b. Oh, sorry, 2 pi on 15. And there is our period. We can also determine something like our median. Our median's that middle point, and in this case, our middle point is going to be 3. So our d value, sorry, I've capitalized all of the variables, so little b. Little d, that's just our median value, and our median value is just 3 meters, and our amplitude is 3.5. Hence giving us those maximum and minimum values we worked out before. So the only interesting point to work out is C. What is the phase shift? C is the interesting one. And so to solve for C, we're actually going to need to do a little bit of work. And the work is coming here. So it says 3 seconds after the water wheel starts turning, P is at its maximum height of 6.5 meters above the surface level. So to solve for this, we're going to need to do some substitutions. So our function currently looks like this. This is what our function currently looks like. We don't know what C is, but we do know that after 3 seconds, D is equal to 6.5. So we can substitute that in. So we get 6.5 equals 3. Alrighty, so subtract 3 from both sides, we get 3.5, because Once again, here we can divide both sides by 3.5, and we're left with 1 on the left-hand side. And once again, we're going to need to work out what happens here. When is cos equal to 1? Well, cos is equal to 1 when this whole thing is equal to 0. All right? We know that to be true. So I can do a quick substitution, and I get that this whole thing, if this is equal to theta, cos of theta, then theta has to be equal to 0. Or some, rotation on it. But in this case, we can just undo that substitution very quickly, and we get 2 pi over 15, 3 minus c equals 0. By null factor law, either this has to be equal to 0 or this has to be equal to 0. And in this case, therefore, c has to be equal to 3. To do our sketch, we're going to use technology, and so we get our final equation. There's our final equation, and now we're going to do it on Desmos. Alrighty, and so here's our model on Desmos. You can see I've replaced t with x, and you can see I found some of the interesting points, the intercepts, the maximums, the minimums, all that sort of stuff. And you can see that the period would end at 15, which is this point here. If I just do a quick x equals 15, you can see that it matches that initial starting height over here. Alrighty, so there's our model. Alrighty, so we've got 2 more questions to answer. So the first one is, how high above or below the water's surface will the point be after 11 seconds? So what we're really interested in is when t is equal to 11, because remember, t is measured in seconds. So we could substitute this into our formula. Typing this into a calculator, we get negative 0.42. And so that would be meters. And in this case, it means it's 0.42 meters below the water. So it's nearly at that minimum number of 0.5. And so then the last part, part D, is at what time does the point P first enter the water? Give your answer correct to 2 decimal places. And once again, if you've got a graph, we're really looking for the first y-intercept, first x-intercept, which is going to be this point here. So 9.2080. That would be where it would first enter, but it does ask for it to 2 decimal places, so we'll round that to 21. And that is the end of the question. Alrighty, so that's the end of our applications of trigonometry. It's quite tricky, some of this stuff. If you work at it, it does get a little bit easier. I'll see you on the next one. Bye-bye.